let's take just a minute and think about what it is that we're trying to learn in this class. So it's physics class. Okay, so we're trying to learn physics. Okay, that's not very useful. What is physics? It's the study of motion, magnetism, electricity, and a whole bunch of other stuff. Still not quite narrowing in on what we're doing in this class. What is physics? It's a mathematical science, and it's based on models. And these models have been developed by the physicists that have been working over the last few hundred years. People like Isaac Newton and Albert Einstein and others that were far less famous. They created these models, mathematical models. And so it's this idea about how the world works expressed as a mathematical equation. So, for example, a model that we're going to use a whole bunch in this class, and if you take second semester, we'll continue to use it in the second semester, is Newton's second law of motion. And this is not a lecture on Newton's second law, so don't feel like you have to understand Newton's second law here. We're going to spend 2 entire chapters talking about it and more. All right, but Newton's second law is a mathematical idea, and it can be expressed this way. The net force is equal to mass times acceleration. Okay, now I'm picking this because I think we all have an intuitive notion of force. We've talked about mass. Mass is how much stuff. We have an intuitive feeling for that, I think. And acceleration, right? I'm gonna mess with your definition of acceleration, but the one that you bring into this class is just fine. So this is Newton's second law. He published this in the 1600s, right? So we're talking almost 400 years ago that Newton first published this. And we're pretty sure that it's a valid law of the universe. But notice that it is mathematical in nature. It is a general principle that we can apply to a variety of situations. Like I said, it's 400 years old. So there were no automobiles in Newton's day, but we can apply this to the motion of an automobile. So, that's probably the context where you've thought about acceleration before. So, what force would give a certain automobile a certain acceleration, right? That's a specific question that we might ask, right? How much force to accelerate or speed up a car? Okay, so this is a general principle, and this is a specific question. This is not a question that Isaac Newton could have asked, because cars were not invented in the 1600s. How do we apply the general principle to the specific situation? The answer is math. Okay. So, if you want to know what is physics, this is what physics is. It's taking a general mathematical principle, doing some math to apply it to a specific situation. What math are you going to have to do here? Well, it depends on the situation, and it depends on the class you're in. In this particular class, this is going to be algebra and trig. Triangles and solving equations. That's what this is going to be. If you were to take calculus-based physics, we'd add calculus to this. If you were to take a more advanced graduate physics class, then we would probably be talking about some other principle than this, and this might be differential equations. It might be any number of advanced mathematical techniques, some of which I have no clue about, right? So, group theory, or there's all kinds of things that could go here, right? But that's the idea. We take a general principle, we apply it to a specific situation, and if we trust our general principle and our logic is correct, then we should trust the conclusions we reach about the specific situation. What are we learning in this class? Well, we're going to learn some of this, for sure. But, you know what, there's only a handful of these general principles. We're going to cover 15 chapters this semester. I'd say there's roughly 15 big ideas that we're going to learn about. That's just not that many, right? The hard part of this class for most students is right here. It's right here. It's doing the math to apply the general principle to the specific situation to get your answer and get your points. This is where most people in my class struggle, right here. So, we're going to take a minute, and we're going to slow down, and the good news is that you don't need a ton of skills in order to get from here to here in this class, right? You don't need a ton of mathematical skills to be successful in the class. The bad news is, without those skills, you won't be able to be successful in the class. So some students have this idea that, well, I'm not that good at algebra, but I can still learn the physics. No, you can't. That's what we're doing, right? The algebra is applying the algebra to the general situation. That's what we're learning in this class, right? This is really a mathematical problem-solving class where we're applying our mathematical problem-solving to physical principles. So, and that's the challenging part of the class. So, the good news is there's not a ton of algebra that you have to be good at. The bad news is you can't learn the physics without the algebra. You just can't. Like, it just straight up can't be done. So, that means that right now, this week, is the time for you to practice this algebra. And again, it's not overwhelming in the sense that I know that if you commit to learning these skills this week, you can do it. And it will set you up for the whole rest of the semester. If you are taking the second semester, it'll set you up for the whole year. And I find that the students who struggle the most in my class are the students who are trying to learn algebra and physics at the same time. It's very hard because those are both challenging subjects. So we're going to ease into the physics part of it. Make sure you got this algebra down. And if you don't, and this goes for everything in this class, but especially the algebra, especially now at the beginning of the semester, if you struggle with this algebra, get help. Practice. Right? Algebra is a skill. It's like learning to shoot a basketball. And if you're no good at shooting a basketball, like I'm no good at shooting a basketball, I don't really think it's because I'm inherently no good at basketballing. Like, I'm no LeBron James, but I bet that if I practiced, I could get better. I feel that very strongly. And I feel equally as strongly that if you practice algebra, you will get better at it. You got to, because that's how we're going to get this through this class. Okay, so what is algebra? Well, we think of algebra as the rearranging of symbols on paper. And it is. I think symbolic algebra is possibly one of the greatest inventions of mankind because it's made all of our modern technology possible. Almost all modern inventions could not exist without symbolic algebra. So I think it is unheralded, but one of the greatest inventions of man. The very first real systematic study of algebra was actually done by this person here. I'm not even going to try and say their name. The greatest, the Greeks made some great progress in mathematics right around 0 BC, and before that 200 BC and before. And then, the European progress on mathematics pretty much ceased. But in the Arabian Peninsula, mathematics was still raging, and people were making great progress. And so one of the earliest texts we have is this one right here from 820 AD, written by this Persian mathematician. Okay, so let's go through what skills you do need to have in order to be successful in this class. Here's one. Solving a system of equations. Solve for x and y. And I guess the first thing to recognize here is if I just had one of these, say I just had this. If that's all I have, can I get a number for x and y? The answer is no, I cannot, because I need to have as many equations as I have unknowns in order to solve for a number. So I could isolate x here, or I could isolate y. But if I isolated y, I'd always have an x on the other side. If I isolated x, I'd always have a y on the other side. So I cannot get numbers for x and y if I only have one equation and two unknowns. I need another equation. So in this case, I have x minus 2y equals 8. Now I have two unknowns and two equations. Therefore, I can get a number out. How should I do that? What would you do? What would your first step be? Why don't you give this a shot on your own? Pause the video and try and solve this. If you get stuck, hit go on the video. The first thing I'm going to do is I'm going to solve this bottom equation for x. Try it on your own. Okay, so I'm going to solve this bottom equation for x. Again, I can't get a number. When I say that, I mean I can isolate x. So, in order to isolate x, I will add 2y to both sides. And that gives me x equals 8 plus 2y. Now I'm going to plug that back in up here. And I get 2 times 8 plus 2y plus 3y equals 2. Notice now I only have one unknown and one equation, so I can't get a number. First thing to do is get rid of my parentheses. Next, I will keep everything with a y on one side, take everything without a y to the other side. I'll do that by combining my 4y and my 3y for 7y. I'm going to subtract 16 from both sides, giving me negative 14. And now we have y equals negative 2. Great. One down. Now I just need to get x. The most efficient way to do this is to go back to this equation right here. Plug in my y here and get a number for x. And there we have it. X equals 4. We need to know about quadratics also. What makes something a quadratic? What makes something a quadratic is that the largest exponent on the unknown is a 2. Notice in this case I have a 2. I do not have a term with just a t. This is still a quadratic. Here I have a term that has an x squared, and this has an implied 1 here, right? So this is implied x to the first power. So we have x squared plus 3x plus 2. This is also a quadratic. Why? Because the largest exponent is a 2. We need to know how to solve quadratics. So here are a couple of examples. In this case, we have these two examples. And again, here we see no t term, but there is a squared term. Whereas here we have both the x squared and the x. Okay, so how do we get at these? Well, if you don't have the squared and the to the first power term, then you can just use manipulation. And we'll do that for this equation here, this green equation. However, if you've got the squared term and the to the first power term, then you cannot just use manipulation, but rather you need to have some sort of tricks in order to solve it. So let's start with this first one. 4t squared minus 9 equals 7. So this one we can solve with manipulation. We'll simply add 9 to both sides. And we get divide both sides by 4. Now what do? Take the square root of both sides. We end up with t equals the square root of 4. The square root of 4 is, of course, 2. Are we done? We are not quite done. There's two ways to get 4 by squaring a number. We can square positive 2, yes, or negative 2. So, our answer is plus 2 or minus 2. Those of you that are going to take the MCAT in your future, watch out for this. This is on every standardized test, practically. Great. Notice we were able to arrive at our answer through manipulation. Just what you think of as sort of your standard algebra. Okay, how about this one? Now in this one, notice we've got an x and an x squared. So you can rearrange this all you'd like, and you will not be able to come up with an answer. Right? You can bring your x, you can try it if you want, but you won't be able to get an answer. In fact, the solution to this requires some trickiness. So as I just said, if the quadratic term contains an x squared or a t squared term, but no x, you could just solve it by manipulation. That's what we just did. However, if the quadratic contains an x squared term and an x term and a constant term, then you need to factor or use the quadratic formula. Now, factoring is a little bit tricky and sometimes requires a bit of a flash of insight, if you will. But quadratic formula is just an algorithm. You just turn the crank. It works every time. So if we're going to try and factor this, notice it's got to equal 0 here. And we need to, in order for this strategy to work, we need to have just a 1 or an implied 1 here. There's no number in front here. You can factor equations that have a number out here. It's just trickier, and I don't want to go into it. For me personally, if I see a number out in front here, I don't even try and factor it. I go straight into the quadratic formula. Okay, so if we are going to try and do this, we need to find two numbers that add to make this, and two numbers that multiply to make C. So we're going to find two numbers that add to make 3, multiply to make 2. Can you think of two numbers like that? I can. 2 and 1. 2 times 1 is 2. 2 plus 1 is 3. And so what we do is we write this like this. And you can confirm this for yourself if you'd like. But if I was to FOIL this out, you'd find that I got right back to here. So these two equations are identical. They're just written a little bit different. Now this has to equal 0. Now remember that anything times 0 is 0. So if this term is 0, the product of these will be 0. And if this term is 0, the product of these will be 0. Therefore, we get 0 when x plus 1 equals 0, which leads us to the conclusion that x must equal -1. And we also get it when x plus 2 equals 0, from which we can conclude that x equals -2. Two answers, which in general is true. We get two answers to the solution to a quadratic. Notice in that previous example, our two answers were plus and minus 2. So keep your eyes out for that. We always get two answers. We just found this by factoring. It's faster and it's easier, but you can't always do it, or you can't always do it easily. So that's why I said earlier, sometimes it requires this flash of insight almost. So if I'm looking at a quadratic, I might give it a few seconds of thought to trying to factor it, but you know what, if it doesn't come to me, I just move on and get out the quadratic formula because it works every single time. So in order to do this, we need to use this quadratic formula right here. And first, let's figure out what our A value is. That's 1. Our B value is 3. And our C value is 2. And so now we plug it into the formula. X equals -b plus or minus the square root of b squared. So minus 4 times 1a, and c is 2, all over 2 times a, which is 1. Again, we get two values. Our two values come from first running plus and next running minus. And again, if we run our calculator, we get x equals -1 and -2. So it's the same answer we got when we factored it. It better be, right? It's just a different technique. So I find often by the time I get to the middle of the semester and I start shooting some quadratics at you, I still see a lot of students trying to manipulate this to get an answer. Remember, you just can't do it. It's just not possible. Okay, we also need to know some trigonometry. And much like the algebra we need to know, the trigonometry we need to know is pretty constrained. We don't need to know all of trigonometry, but there are a couple of skills we're going to use over and over and over again. And so let's get good at them right now. Here are some facts. If we add up all the angles in a triangle, they all add to 180 degrees. That's not just this triangle, it's every triangle. Every single triangle, the internal angles add to 180 degrees. Often in this class, we will use radians. Pi radians is equal to 180 degrees. Oh, here in a few chapters, I'll spend some time talking about why we use radians, why they really are a very useful unit. For now, we're just going to kick that down the road, and we're going to just want to remember that pi radians is 180 degrees. Most of the triangles that we're going to be dealing with here are right triangles, and when they're not, we're usually going to break them down and try and find the right triangles within them. So we need to know how to do our right triangle trigonometry. A right triangle is a triangle with one angle equal to 90 degrees. So if we have a right triangle where one angle is 90 degrees, then we can use the Pythagorean theorem. A squared plus b squared equals c squared. One of the oldest mathematical theorems around. Nobody actually knows who came up with this. It was not Pythagoras. Pythagoras was the first person to publish it, but he did not come up with it. So we don't know who came up with this, but it's a pretty cool idea. And something that you're probably familiar with. Now, something that you've probably learned before, but may or may not struggle with, is using sine, cosine, and tangent. And there's a lot of mnemonics to help us remember this. Most folks, I feel like, learn so, ka, toa. I learned, oh, happy, another hour of algebra. So there's that. Some old hippie caught another hippie tripping on acid. Maybe that works for you. I don't know. There's a lot of mnemonics here. But what they help you remember is this set of equations. I find often students remember SOHCAHTOA, but they don't remember what it's trying to help them remember, which are these three equations. These three equations express relationships between the different sides of the triangles. Notice they are always relative to which angle we are talking about, because we're talking about opposite and adjacent. And opposite and adjacent depend upon whether I'm talking about this angle or this angle here. Now in this drawing, I've identified this angle here. My opposite is opposite to that angle, and my adjacent is next to this angle. The hypotenuse never changes. It is always the longest side. Notice, however, that if I instead identified this angle right here, now which side is my adjacent? Which side is my opposite? Well, I've switched angles, so this side right here is now my adjacent, and this side over here is my opposite. Of course, the hypotenuse doesn't change. It is always the longest side. Let's practice using these relationships. Okay, find x. Oh, there it is. Found it. That's not what I mean. What is the value of x? That's probably what I should have written. Here's our right triangle. First off, we want to identify which is my opposite and which is my adjacent. Think to yourself, which is? Is x my opposite or my adjacent? X is my opposite because it is opposite to the 28. This side down here is adjacent. I'm not asked about it. I'm not given it. So I'm not going to worry about it. So what we have here is opposite, hypotenuse, and theta. What we do is we look back and we try and find the equation that has two things I know, one thing I don't know. The thing I'm looking for is opposite. The thing I have is hypotenuse and the angle. I see here that the only one of these three that has the angle, opposite, and hypotenuse is the sine equation. So I want to use sine. So I will write sine of theta equals opposite over hypotenuse. Now I can do some quick algebra to find x. X equals 4 sine of 28 degrees. I run my calculator, and I get an answer that is 1.9. In this one, I'm asked to find c and alpha. I can do that in any order I want to. I can find either of them first. I'm going to go ahead and find alpha first. So notice here, if I look at alpha here, okay, 2 is what? Adjacent or opposite? Opposite, right? And the 5 is my adjacent. So we see here that I'm looking for the angle, I have opposite, and I have adjacent. So we go back to our SOHCAHTOA list. Which of these equations has two things I know and one thing I'm looking for? Well, the tangent does. The tangent has opposite, adjacent, and angle. So I'm going to go ahead and write that the tangent of theta equals opposite 2 over adjacent 5. Now, a mistake I see some students make is divide this by tangent. And this does look like tangent times alpha, I agree. But that's not what this means. That's not what this notation means. What this notation means is tangent of alpha. In other words, tangent is a function. We undo it, not by dividing it away the way we would if it was a number or a variable, but we have to use the inverse of it. And so we say that alpha equals the inverse tangent of 2/5. You may see this written as the arc tangent also. So it could be written as tangent to the -1, atan, or arc tangent. Any of those express the same idea. Now I just run my calculator. On most calculators, you will hit second and then the tangent button. And that's how you'll find your inverse tangent. When I run my calculator, I get 21.8 degrees. And I encourage you to run your calculator and confirm that you also get 21.8. How about C? Well, at this point, now I know the angle and two sides. Boy, I could find this in a number of different ways. I'm going to go ahead and use the Pythagorean theorem. A squared plus b squared equals c squared. That means that c equals the square root of a squared plus b squared. And when I run my calculator, I get 5.4. Not too bad. I find most students feel pretty comfortable with the Pythagorean theorem. At this point in the semester, I always get questions about significant figures. How important are significant figures? How much of a stickler on significant figures am I going to be? I want to spend just a few minutes and talk about that. So I guess the first thing to say is that significant figures are very important, and they allow us to report sort of how precise our measurement is. What do I mean by that? Well, let's do a real quick experiment. Here I have a pen, and I have a ruler. And I'm going to measure the length of my pen. Okay, so I get this out and I go here, and I did this previously. I'm recreating this experiment for you. This is not live action. This is a recreation. 14.3 centimeters, just like it says on my PowerPoint. Okay, 14.3 centimeters. Great, I'm done, right? Well, how close is that to the actual value of how long this pen is? Well, let's assume that I'm a competent ruler user. And let's assume that I didn't just, screw up and put it out here in the middle somewhere, or something like that. There's any number of errors I could make. And let's assume that I'm a competent pen measurer. So I got 14.3 centimeters. Could I do a better job? Well, sure. I could get a more accurate ruler, right? This ruler is marked to the millimeters. And so that's a tenth of a centimeter. That's where I got that 0.3. By getting out my magnifying glass, I could probably guess another decimal. So maybe I got 14 point. It's actually kind of maybe 14.35. Is that as good as I can do? Well, I could get a micrometer or something that a set of calipers, and I could probably add a couple decimal places. Is that the actual value? Well, no. I mean, because I could get a more accurate machine. There's this really precise measurement that uses diffraction of light and things like that. I could come up with a more accurate value than 14.352. Can I keep doing that though? How long could I keep doing that? Well, almost indefinitely, right? So it's a weird thing to think about. But what is the actual value of how long this pen is? There is no answer to that question. There is no actual value. There is only increasingly accurate estimates. Now, atoms are about 10 to the negative 10th, meters across. So That's 10 to the negative 8 centimeters. So really, I only get 8 decimal places before I'm talking about the width of an atom. And atoms are kind of fuzzy things. They're these electron waves around nuclei, and they don't really have precise edges. So what's the exact value for how long this pen is? There's no answer. That doesn't have an answer. So significant figures, though, give us a way to say, well, okay, there's no exact value, but how precise was my measurement? And so when I say 14.3, that's telling you how precise my measurement is. Let's see how that idea can cascade through some math and why we have to be careful about significant figures whenever we're doing math. Let's do a real quick physics problem. This is an actual physics problem. This is the kind of physics problem I might actually ask you in chapter 18. This is a chapter 18 physics problem. You can do it today, I guarantee. Okay, so I'm going to stand my pencil up vertically. Pen, it's a pen. Okay, standing this writing utensil up vertically. When the sun makes an angle of 30 degrees with the vertical, so there's my pen, here's my sun. The sun's rays come down like this, and this angle right here is 30 degrees. How long is my pen's shadow? I'm looking for this right here, and this side right here I know is 14.3 centimeters. Okay, so 14.3 centimeters here. I'm looking for the length of my shadow. Pause the video. See if you can do some trig. Did you pause the video and do it for real? Because you should have. Okay, let's do it together. Here's my triangle. I know the angle. I know adjacent. I'm looking for opposite. The trig function that has an angle, adjacent and opposite, is the tangent. So I'm going to write the tangent of theta equals opposite over adjacent applied to this situation. The tangent of 30 degrees equals opposite x over adjacent 14.3 centimeters. Some quick algebraification gets me the result. X equals 14.3 centimeters times the tangent of 30. And I run my calculator, and I get that x equals, here we go, 8.256 108 849 centimeters. Okay. That's my answer. My calculator told me that's my answer, so it must be right. But let's look at this. How big is an atom? An atom is about 10 to the negative 10th meters across. That's 10 to the negative 8th centimeters across. So let's count 8 decimal places. 1, 2, 3, 4, 5, 6, 7, 8. That's 8 decimal places. So if I report my answer like this, then I am telling you that I know how long the shadow is very precisely. In fact, I have a resolution on how long the shadow is that is better than the size of an atom, right? I say, well, you know what? It's about some number plus 0.9 of an atom. That doesn't make any sense. We only knew how long my pen is to 1 decimal place. How on earth can I know how long its shadow is to better than the size of an atom? How can I know that? The answer is I don't, right? I only made one measurement, right? The measurement was of the pen, but the precision of my measurement of how, or in other words, how well I know the length of my shadow cannot be better than how well I know the height of my pencil, because the length of the shadow is based on my measurement of the pencil. So all of these numbers over here, I know my calculator told them to me, but they're kind of a lie. They're a lie, right? They're a consequence of the fact that tangent 30 is an irrational number. It's an infinitely long, non-repeating decimal. And so this actually goes on forever, right? I can program Excel to give me as many decimal places as I want. And I could write this out to 100 decimal places. That doesn't mean that they mean anything at all, right? In fact, if I knew how long my pencil was to 3 significant figures, which is what I know here, right? 14.3. That's 3 significant figures. Then I can only know my answer to 3 significant figures. So I really should write this. X equals 8.26 centimeters. If I include any of this business, in a way, it's a lie. I don't think it's exactly unethical, but it's not real. That's for darn sure. So that is the point of significant figures. That's why we care. That's why they're important. It is an important idea. Now, how do you count sig figs? Well, I'm going to go through that pretty quick. When you multiply numbers, your answer should have the same number of significant figures as the smallest, the least precise of the numbers you're multiplying. So here I've got 3 sig figs, 2 sig figs. My answer should have 2 sig figs. Same thing here, right? I had 3 significant figures going in. This has an infinite number of significant figures. Therefore, we use the lowest, which is 3. We should report our answer here. When we add number, we keep the number of decimal places as the least precise. Some numbers have no uncertainty, and that would include tangent of 30, pi, number 2, things like that. Now, this is all sort of to say that I think that significant figures are important, but I have more important things to teach you in this class. And so I'm honestly not going to get worked up about significant figures. You will never lose points on my assignments if you use the incorrect number of significant figures. However, your homework is done on mastering physics. Mastering physics is computer, and it is not as flexible. So, mastering physics will never mark you wrong for putting in too many significant figures. However, if you use too few significant figures, you may get the answer wrong, not because you use too few significant figures explicitly, but because those too few significant figures made it so that you rounded outside of the acceptable tolerance for mastering physics. What I mean by that is that the default in mastering physics is that if your answer is within 3% of the correct answer to the correct number of significant figures, then it marks your answer as correct. If you are outside 3% off of the correct answer, then it marks you wrong. So the best way is to keep multiple significant figures, more than you need, in intermediary steps, and in the end, round to the correct number of significant figures, and that will get you the correct answer. Now, again, with mastering physics, it's not going to mark you wrong for too many significant figures. It's just not going to do that. But it is possible to get it wrong for keeping too few significant figures. And so, just keep an eye on how many sig figs are in the problem. Most of the time it's 2, right? So generally speaking, keep 4 decimal places in intermediary steps. That way, when you get to the end, you'll still be within that 3% tolerance. Some of the most frustrating times my students have had is when they know they're doing a problem correct, they've got the answer, and mastering physics keeps telling them they're wrong, and it's simply because they've rounded too early in the process. They've rounded too early in the process. By the time they did 3 or 4 more steps of algebra, they were outside that 3% tolerance, even though all their steps were correct. So, that's a long way of saying, you got to kind of keep a mind on them, but I have more important things to teach you this semester.